All right, greetings everyone. So here's some homework help for section 2.1, numbers 5 and 9, since we weren't able to finish all of these in class today. So question number 5, we're given the height of the ball. It's this equation here, y equals 40t minus 16t squared. And we're asked to find the average velocity of the ball over different time intervals. Now, the key thing, it says that the time intervals begin at t equals 2 and they last, or they're lasting, this long and this long. So my first interval in which I'm calculating the average velocity starts at 2 and then goes to 2.5. And then my next interval, that's for up here, and then my next interval for this one over here starts at 2 and goes to 2.1. It lasts 0.1 seconds. So in order to calculate our average velocity, we're just going to do what we were doing in class. In this case, instead of using s like we did in our notes, because s was the position function in that example, y is our position function here given the height. So it'll be y of 2.5 minus y of 2, and then that quantity will be divided by 2.5 minus 2, the width of the interval. And so you just go plug 2.5 into the function over here for the function y for t. Plug 2.5 in for t. Plug 2 in for t as well. Take their difference and divide by 2.5 minus 2. Now, the other thing that you need to do is in part B, you need to estimate the instantaneous velocity at t equals 2. Notice in part A, the intervals are being made smaller. They're shrinking from 0.5 to 0.1 to 0.05 to 0.01. From the values that we're obtaining by shrinking the intervals, hopefully you'll be able to recognize some sort of pattern in the numbers. They look like they're approaching a certain quantity. Whatever pattern you think they're approaching, or it looks like they're approaching, that will be your estimate for the instantaneous velocity when t equals 2. And so just look at the pattern of numbers and see what happens. Now for number 9, we're dealing with this curve sine of 10 pi over x. And this curve that we're dealing with here is similar to the one we did in our notes, the very last example. The difference here between this curve and the curve from the notes is we have this extra factor of 10 pi. That's in the numerator. Instead of a 1 over x, it's 10 pi over x. So it's very similar to that curve. So remember, in our notes, that curve right around the y-axis bounced up and down an awful lot and was doing, was some pretty crazy things up here in the middle. Okay, so it's the same type of thing happening with this one. Now, I'm going to get rid of all that mess for a moment. So what we have to do is calculate the slope of a secant line, okay, which is what we've been doing a lot of, between the point 1, 0 and the point Q, which is given by x sine 10 pi over x. And you're going to use these values in here for x. I'm not going to write down much for you to do on that one. I want to talk about the other parts of the question. Set up the slope of the secant line equation, change in y over change in x. And then when you set that up, you'll be able to hopefully see a pattern. I'm sorry, I got off track there. When you set up that, put those numbers in and calculate your slopes. You won't see a pattern in this one here. And that's what part B is addressing. Now notice this little icon over here. That means you're supposed to be using some sort of graphing technology, so you can go to Desmos.com or use your graphing calculator if you have an app on your phone. It doesn't matter. But it says use the graph of the curve to explain why the slopes of the secant lines in part A are not close to the slope of the secant line at P. All right, so because of the way that this graph is behaving, because it is bouncing up and down so much as the values get closer in here like this, they're just going up and down like crazy like this. Now, I'm not doing this to scale, so bear with me on the picture here, but let's suppose that this is 1, 0 right here. If that's 1, 0, the values that we're choosing, there's really gaps in here, and I drew these kind of close together. The points that we're choosing are so spread out that you're getting points that are, for instance, in these values here. So if I was to draw a secant line between a couple of these points, like this one that was bad. Here, let me do that again. These two over here, or these two over here. You can see these secant lines have very different slopes, and it'd be hard to see a pattern happening here. Again, that's because the x values that we're choosing, that they chose for us, I should say, all of these x values given in part A, they're too spread out, and the curve is jumping around too much in between them, and since it's jumping around so much, you can't see a pattern based on the slopes of those secant lines. You need values that are closer together. So part C says, by choosing appropriate secant lines, estimate the slope of the tangent line at P. So you don't want values that are going to be on other parts of the curve after the curve's gone up and down after a certain point. You want points in the curve that are, these are going to be in yellow, that are all going to be, say, on this branch of the curve right here, so that they can be used to make a good prediction. If the graph goes up and down a whole bunch and you choose points after it's gone up and down a whole bunch of times, then the values you're getting cannot be used to make a good educated guess about what the slope of the secant line, rather the slope of the tangent line, will be. So choose smaller values of x, and find a good graphing technology to help you do that. Desmos would probably be the best thing to do in order to work that out. Well, go study.